Now we're going to take a look at the electric potential due to a point charge. So in order to find the electric potential at point P, due to a point charge, we must integrate. So the first question we're going to ask is why we even have to integrate. And that's because the electric field is going to vary along the path. So that means the work that we do will change as well. So then the simplest path would be a straight line from infinity to point P. So let's try and figure out how we can approach this and then try to solve. The first thing we know is that there's going to be some existing charge Q that's there. And I'm just going to draw this line extending to infinity. I'm going to put in a point P here, because that's where we want to move our test charge to. And I'm going to say our test charge is currently at this location and it's moving tiny baby steps dl along the path. I also want to mention that this, we'll call this distance that Q is already at R prime, and we'll call this R. Okay, so I want to take a look at this test charge first. So I want to say that we have already reached a point R prime away from Q, and we take a small step dl towards Q. What can we calculate over here? We can calculate the electric field. So it experiences an electric field. So we define that as E being equal to K, or 1 over 4 pi epsilon naught, the charge Q over R prime squared, R hat, or not R hat, but R prime hat. Okay, so after that, we know that the differential potential is going to be equal to E dotted with dl. Okay, so we have the first thing, our differential element constructed, and now we have to figure out what EDL is. So let's take a look. We'll call this number 2. We need to define E dotted with DL. And remember, we're trying to find the electric potential due to a point charge, and we're going to end up with an equation afterwards that we can use. So let's start here with our charge Q. It's a point charge, and it's going to have an electric field around it. We'll draw this as the first one, and then there's more and more radiating out like this. And let's say that I have my test charge that I want to start here at point A. And I want to move it over to point B somewhere over here. So that means we have to consider EDL. DL is going to be a part of the path that it takes, but we know that the electric field is a conservative field, so it doesn't matter what path it takes. So let's just go with a general case like this, which means at any point in time, our test charge Q could be here. We're going to say that this is RA, this is RB, which means this is going to be R in the R hat direction. So for our general case, in green, I'm going to draw this as the differential path element. And I'm going to extend the line for R so that we can define an angle theta between R and DL. The next thing I want to take a look at is just this area here. I'm going to zoom in. We have the imaginary line extended from R, and then we also have our path DL. Just make this So this is what we have, and that means we can define this as a change in radius or path. We're going to call this dr. And just remember, we have our test charge Q at this point. And let's see what I'm trying to find. Okay. So here, oops. Q moves along the red path from A to B. In a general case, moving DL along the path and making an angle theta with the electric field vector along R. So what we know from this, we know E is dotted with DL, which means we have E DL cosine of theta we have E dl, and then we have to figure out an expression for cosine of theta. So in terms of this, we are going to get some sort of value of an angle over here, and we can get cosine of that angle, which is adjacent over hypotenuse. So that would be dr over dl. And then we have E dl. The dl's cancel each other out in this case. And we have E dr, which is a scalar quantity. So the last thing we want is to say we have a point r prime away. So we have to say that our E dl is going to be equal to E dr prime. So now let's put it all together. We're going to have VP from step number 1 is the negative integral from infinity to our point R, because we're trying to move it to point R, E dl. We know that we can rewrite E dl as E dr, but in our case, we have infinity to r of q over 4 pi epsilon naught r prime squared dr prime. And if you solve that using limits and integrations, you're going to end up with q over 4 pi epsilon naught r. So therefore we have an equation for the electric potential due to a point charge, and that's q over 4 pi epsilon naught r. So we'll say electric potential due to a point charge. Now let's take a closer look at this and see if this makes sense and what kind of information we can get from this. So if we have a positive charge, this implies that our electric potential is going to be positive as well, which means if I'm bringing a positive test charge towards a positive charge, it's going to be repelled, and that means I'm going to do positive work. So repulsion means positive work. On the flip side, if our charge is negative, then our potential is going to be negative as well, because an attraction is going to mean negative work. So these are important trends and patterns to notice, especially after you solve for the electric potential.